Hey everybody, welcome back. So I'm going to run another quick demo video here, and we're going to talk a little bit about linear regression using ordinary least squares algorithm and how we can implement that in terms of Jupyter Notebooks, Python, scikit-learn, NumPy. So my apologies as my camera wiggles as the cat is making his presence known. You might get a glimpse here in a minute. But yeah, let's take a look. So once again, these notebooks are available on GitHub. You can find them right here in the notebooks directory. And the Git repo UCSD cogs 118a. So we're going to look at lecture 03, linear regression, and I've already opened it up on the Google Colab. So let's begin. So here we have the general usual stuff we're going to import throughout most of these demos. We're going to use matplotlib for some graphics, and scikit-learn we're going to grab from the linear model module, we're going to get linear regression. And from pre-processing, we're going to get something called polynomial features, which we'll talk about more in a minute. So I've just defined some quick functions here, which let's just kind of remember that what we have here is that all the basis of linear regression is that there is some true underlying process. Okay, something, for instance, defined by a line if we're doing linear regression, and that linear process is corrupted by Gaussian noise, right? So there's going to be a Gaussian distribution around that line of regression. So what we're doing here is we're taking some function and we're going to lay down that function from 0 to 1, and we're going to take the true function value and we're going to corrupt it with just a normal distribution on top of it. Okay? And I've defined a bunch of toy problems here. Oh, here comes the cat. Maybe Magic, would you like to say hello? This is Magic. Say hi, Magic. You up? All the way. There you go. Yeah. Magic has been in this position before doing videos with me. He recognizes himself on camera now too. Yeah, a couple of months ago he started batting his own image on the screen. All right, down. Thanks. Yes, you can't see yourself. You're trying to bat your own head again. Good job, kid. All right, let's get back into the demo because you're paying for knowledge, not cat videos. All right, so today we're going to do a linear function, obviously, right? So here's an underlying linear function we're going to corrupt with some noise. We're going to take, oh, thanks for that key press, Magic. I'm sure that happened while you were doing your stuff. We're going to take 10 samples out of this data, and we're going to corrupt them with a standard deviation of 0.3. Oh yes, thank you, Google. I really appreciate your... Okay, did we get that? Yes, I have signed in. Wants me to leave the page. Great. Oh, fantastic. Fortunately, y'all can't see, so, you know. But you all go through this every day, I know. I've got some real good luck going with my demo so far, so. Right, we're logged in. Yes, I know it's not authored by Google. Thank you. All right, so let's generate some data. All right, we're gonna grab that toy data using a linear model, and we're gonna get the true stuff coming out here. This is the reality, and we're gonna plot both the reality here in the green line, and we're also going to plot the random noise corrupted data there in the blue dots. Okay, so this is what is truth. This is not a linear regression. The green is the line of truth that generated the data. The blue is the corrupted version of the data with a little bit of noise added in, right? And now we're going to fit a linear regression to those blue dots. But before we get to that, I want to introduce an idea, okay? So we have along this x-axis an x variable, right? So the horizontal axis of this training data here, this training data plot is x. Now, a normal linear regression, we would just do y is equal to mx plus b, right? But we might want to, for instance, fit more than just x. We might want to fit, instead of having y is equal to mx plus b, we might want to put in to the x itself. Remember that x is a vector in our conception, right? It's not a single variable. So we can make a vector which has, or not a vector, but a matrix, right? We can make two columns. We can make a column which has the bias term, this first column here, and it just has a constant 1. And so any weight on that constant 1 is equivalent to the bias term, right? And here is just the x value in the right-hand column, right? So the x value is 0, and then it's 0.1 and 0.2, 0.3, et cetera, all the way up to 0.1. Sorry, 1.0. All right, so great. What we've done here is we now have turned what was just x, right? X train is just x, 0, 0.1, 0.2, 0.3, blah, blah, blah. All right, and we've turned it into a degree 1 polynomial, where a degree 1 polynomial is this, 1 plus x, right? What if we wanted to turn it into a degree 2 polynomial? Well, we just call polynomial features with degree equal to 2 here. We pass in that x train vector, which is just 0, 0.1, 0.2, blah, blah, blah. And now we have this, 1 plus x squared, where, again, samples are rows. So this is one sample. It's the sample where x equals 0. This is the sample where x is equal to 0.1111, right? Where we have 1 plus x squared, and so on and so forth. All right? So we have transformed a single variable x into 3 variables, in this case, 1 plus x squared in 3 separate columns. All right? I want to put that on hold for a second because we're going to go back to doing just this. We're going to go back to doing just a 1 plus x. Why are we doing this? Well, what we're doing again is we're pulling the bias term that could be a separate variable into the x vector itself. So we only really have here that y is equal to w transpose x, which I just did that backwards, x transpose w. Good job, Jason. All right. So, so now we're going to show you how to use NumPy to solve the analytic solution for ordinary least squares. Recall that in these previous lectures, we've done the derivation of the ordinary least squares analytic solution. So because ordinary least squares is a function which is convex, it has just one and only one minimum, right? At the bottom of that convexity. Wherever the derivative of the loss function is 0 is the minimum, and that minimum is the one best possible choice for the weight vector. All right? And we did in lecture, we showed you how to get to this answer. There's, we're going to solve for w in terms of the inputs x and the targets t. Okay? So let's do that. We have those x variable, right? So we're going to create the design matrix x train just like we did a minute ago. Okay? So again, this is just 1 plus x. Okay? We have a bias term built in on here. Well, this right here is the math shown here, the final analytic solution. The inverse of xtx multiplied by x transpose, sorry, dot product with x transpose, dot product with the vector of labels t. Okay? How does this work in NumPy, right? So this is the inverse of a matrix. Okay? So that's the matrix inverse to the -1 there. So we call that around x transpose, which we dot product with the original x. Okay, and all that goes into the inverse, right? Then we take the result of that inverse and we dot product it with x transpose again. And we dot product it with the labels, with what we called target t in the math. And here it's called ytrain is the variable, which is the actual true values. All right, so let's go ahead and solve it. So this is the bias term, 1.3. This is the slope, which works out to be 2.79. And that's kind of close to the right answer, but not exact. So I'm curious if you can think of why it's not exactly the correct generating function. I can't hear anybody. Right? So, of course, why is that the case? Well, because of this. If we just fed in data that laid along that green line, then we would get the right answer. But because we fed in the blue dots, which are corrupted by noise, that's why we get an answer which is close, but not quite correct to the true generating function. So this gives you an idea of the challenges in machine learning, right? The challenges in machine learning, we always know that our data is corrupted by some kind of noise, be it random or sometimes systemic, right? Stuff like that. We know that we have problems and we're trying to estimate a truth that we cannot see. All right. So for those of you who are following along, you might be interested in this sequence of cells where we just do piece by piece by piece, okay? So you can see, especially if you're just a little fuzzy on the linear algebra, what it means to take the transpose of the original training, what it means to take that transpose and then dot product it with the original x value, x matrix, right? So you can see the row column math piece by piece as we then inverse that and then take the dot with the transpose again. And then finally the full solution to solve for W once we dot it with the target vector. All right. We did our first machine learning algorithm completely manually, right? You just did it by hand from the very beginning. There is, of course, an easier way. So scikit-learn is going to be our standard library. It implements lots of algorithms for you, so you don't have to do this low-level stuff. And even more so, what they care about is all the various ways in which you can make this speedy or avoid numeric errors during the calculations, stuff like that, okay? These are topics that you might explore if you took classes like an optimization of convex functions or a discrete mathematics class, right? You talk about ways in which you might be trying to calculate a derivative but make tiny, tiny errors, or integrals even worse, make tiny, tiny errors that will add up and suddenly you'll get the wrong answer after a lot of iterations, right? So these are the kinds of things that scikit-learn takes care of you, the implementation details, and they make it fast. So how does scikit work? We kind of talked about this back in lecture 2 feature selection. Every single thing in scikit is a class. Its base class is an estimator, and the estimator has certain methods, okay? So the thing you'll use the most is the fit method. So we grab a linear regression, and critically we tell it, don't fit the b, don't fit the intercept, don't fit the y-intercept. Why are we telling it that? Anybody have a reason? Yes, indeed. I hear somebody in the third row singing out, because we already built the bias term into the X matrix. Okay? If we allowed it to fit a separate intercept, a separate B, we would have two bias terms, right? We don't need that. So we tell it, don't fit a separate bias term. We've already got that handled. So we're going to fit the regression saying this is the inputs, these are the correct labels for those inputs. Out we get is a set of coefficients, and they are exactly the same coefficients that we calculated manually. All right. So before we go, because you have now implemented linear regression OLS style in two different ways, I want to go mention one other thing. All right, remember those polynomial features where we could pass in not just 1 plus x, but 1 plus x squared or cubed or whatever? We could pass in polynomial functions. Well, this is the way you can use ordinary least squares to fit not a line, but any polynomial curve you would like to fit. Okay? Ordinary least squares is a linear method, but it's not linear in x. It's linear with the w, with the parameters, right? So if your inputs are x squared and x cubed and so forth, then you can fit quadratic and cubic and so on polynomials, because your partial is with respect to the w, okay? That's what you have to have be linear. Right, so all we do is we feed in squares and cubes and so on, and then we can fit polynomials in x. All right, what does that look like? Well, we're going to take our same data, the same 10 training data points, okay, which are this true green line corrupted by noise, and that's the blue dots, okay? Here at m equals to 1, at a degree 1 polynomial, you can see the line of regression that we fit in red there. So green is truth. That's the generating function. Red is the linear regression that we came up with, which is not quite truth, right? We saw that in the numbers of the w's, but we can also see here how it lays across the true line green in a slightly different way. Okay. What is a zeroth order polynomial? Well, it's fitting only a bias term, so only a constant. So we have this horizontal slope, zero slope, right? And what happens when you fit a bias term, what you're fitting is actually the mean of the y values in the training data. So that red horizontal line at m equals 0 at a zeroth order polynomial, that is just the mean y value of those blue dots. Okay? So then you can see a cubic function and a ninth order function right down below, fitting what's underlying linear data. Now, I ask you, which one of these four curves, right? If you didn't know where that green line was, you're blind to that green line, just kind of erase it from your mind's eye, right? Which one would you think was the best fit? I mean, it's pretty clear you're not going to pick zeroth order or ninth order, right? They clearly are doing bad things that don't seem to fit the data. Everybody knows that it's actually a linear function. It's hard to erase that from your memory, but you can see here that the third order doesn't look that bad, right? If you really kind of erase that green line from your mind's eye, you could maybe squint and say maybe it is kind of tapering off and going that way, okay? So we have two semi-reasonable models, if you're not aware of truth. And we have two very obviously bad models. Well, let's talk about the obviously bad models. The zeroth order is doing what we call underfitting. Okay? It's not taking enough advantage of the training data. It's not fitting the training data well enough. You can see that it's clearly not capturing elements of what's going on. The ninth order has enough degrees of freedom, right? It's 10 data points. So n minus 1, by the way, is the number of degrees of freedom in a system of equations there, right? It can exactly fit perfectly all of the 10 training data points. Okay? It has enough degrees of freedom to perfectly hit all of them. So obviously, if we pulled out new data from the same underlying distribution but a different set of random corruption to it, this ninth order polynomial is going to fit very, very badly. So this is overfitting. This is taking too much information from the data. We are fitting the noise in the data, not the underlying process. Okay? So these are critical elements that you probably have already got a firm grasp on. You took 108, your stats class, you probably already have a good idea of underfitting and overfitting. But if this is your first experience with underfitting and overfitting, you have to really understand these concepts because we're going to come back to them over and over and over again. Okay? So zeroth order polynomial is not capturing important aspects of the process. The ninth order polynomial is capturing noise, and we don't want that either because we're going to be doing bad when we see a new version of the same data. Okay? It's going to be true in both the zeroth order and the ninth order case. When we draw new data, we're going to be doing badly in different ways. All right, we're definitely going to talk about that in lecture on Friday, and I hope that we will see you all there. Hasta.